All right, so whereas the last few lessons were primarily focused on understanding exponents of different types and moving towards rational exponents, now the focus of this lesson and the remaining lessons really are going to be more and more on understanding radicals. And remember, any exponent that's a rational number can be expressed in terms of a radical, but radicals will now become the focus of the remainder of this unit. And so looking here, I have 3 different radicals. They're all types of square roots. And so these radicals, what we can write as a mixed radical. So what's a mixed radical? Well, let's look at 45, root 45. The number 45 is not a perfect square. So the square root of 45 is not a rational, nice kind of tidy number. But the number 45 is the same as 9 times 5. And so I can rewrite root 45 as root 9 times root 5. And the key idea is I can then break this up into root 9 times root 5. And these are all equivalent. And if you go this way, again, if I'm multiplying 2 of the same type of radical, I can put them into a single radical. So the square root of 9 times the square root of 5 is the same as the square root of 45, and vice versa. That's it. The whole point of doing this is that 9 is a perfect square, so I can rewrite that as just 3 times the square root of 5. Oh, it's still a bit messy. There we go. I guess that's good enough. And so the key is, as soon as I got to here, I could write that as a separate root. And I chose to do that because I knew 9 was a perfect square. So what we call here at the end, we call this a mixed radical, or a mixed, just mixed radical. And we call this an entire radical. And you can always go this way, and you can always go this way. All right, so root 72. Again, I need to think about how I can think about the factors of 72, what numbers multiply into 72, but not just any numbers. I want one of them to be a perfect square. And so again, I could go 9 times 8, which is totally fine. Root 9 is exactly 3 whole. That's it. If I stop there, I'm just not done. And that's because 8 has another perfect square inside it as a factor. And we're not really done until I've taken out all the perfect square factors. And so if I chose to start with root 9 times root 8, then I'm just not done yet. Although I will mention afterwards there's a slightly faster way I could have looked at this. That said, root 8 is the same as root 4 times root 2. So now I have 3 times the square root of 4 times the square root of 2, which is the same as 3 times 2 times the square root of 2, which is the same as 6 times the square root of 2. So that's the answer I really want to get to. That's the mixed radical we want to get to. And so root 72, the square root of 72, is the exact same as 6 times the square root of 2. That's it. I could have done this a bit faster if I chose in the very first step to break it up slightly differently. So let me show you another way of approaching it. Let me go back to root 72. That said, 9 and 8 aren't the only 2 numbers that multiply to 72. And 9 is not the only perfect square inside the square root of 72. It's also the same as 36 times 2. 36 times 2 is 72. And if you thought of that, then we can get to our final answer a lot faster, because the square root of 36 is exactly 6, and now we're done. 6 times the square root of 2. And so if I look at that work, yeah, the second approach was a lot faster. Although, if I ask someone to tell me 2 numbers that multiply to 72, I don't usually expect to hear 36 times 2 right away. Although again, it's not ring correct. So we want to move away from just having constant values to having variables. And so what about the square root of a cubed? Well, same idea. I'm going to break up a cubed this time into factors that are perfect squares. And so a cubed is the same as a squared times a. And a squared is a perfect square, hence we say a squared. Which means I can break this up into the square root of a squared times a. And the square root of a squared is just a. Well, there should be a square root symbol right there. And again, if that seems strange, there's a couple ways you could think about it. You could think about a square root and a power of 2 as being inverses of one another. They undo each other. They cancel each other out. Just like plus 2 and minus 2 cancel each other out. They're inverses of one another. You could also just think about this statement, the square root of a squared. That means the square root of a squared means what number times itself equals a squared? Well, that number has to be a. Either way, I can simplify expressions that have constants or variables in them. And again, what I have at the end, this is my mixed radical. And this was my entire radical. However, I want to make one more comment about this last one. Again, the more connections we realize, the more options we have. Another way of getting from here to here is using exponent laws. So let me kind of make a note right here. If I go back to my first, what I started off with, it was a square root of a cubed. Well, using what we learned about exponents, I could rewrite this as a to the power of 3 over 2. Which, a to the power of 3 over 2 is the same as a to 1.5. 3 over 2, same as 1.5, 1.5. Well, 1.5 is the same. This may seem kind of silly, but the number 1.5 is the same as 1 plus a half. That's what 1.5 means. And I'm adding numbers inside my power, which means I can write this using exponent laws kind of backwards as a to the power of 1 times a to the power of a half. And for some reason, again, my marker went super thick. And what is a to the power of 1? A. What is a to the power of a half? The square root of a. And notice if I look at that, it's the exact same thing we had before. I'm not saying what I just did here is any better, but I really want to point out everything we've learned about exponents, we can connect to radicals and vice versa. Just tons of connections here. Although, if I had, I kind of like what I did originally better, but it's all connected. All right. So I think I just have it now the other way around, yeah. So now I'm giving you mixed radicals. I want you to write them as entire radicals. And so let's look at 3 root 10. Kind of the reverse of what we did before. I want to take number 3 and I want to write it as a radical. So I have to think the square root of what equals 3? Well, the square root of 9 equals 3. Once I have that, I am multiplying 2 of the same type of radical. So root 9 times root 10 is root 90. And again, here is our entire radical. Here was our mixed radical. Again, just the reverse of what we did last time. And so similarly over here, 4 root 5. If I want to write it as an entire radical, I need to change 4 into a radical. So I need to think to myself, the square root of what equals 4? Well, that's the square root of 16. Now I can just think, what is 16 times 5? That is 80, so the square root of 80. So the square root of 80 is the same as 4 times the square root of 5. And lastly, like before, what if we have variables? And so I need to change a squared into a radical. So the square root of what equals a squared? A little bit harder, but same idea. The square root of a to the power of 4 equals a squared. And again, if you're unsure, just double check. A squared times a squared does equal a to the power of 4. Once you have that done, then I'm multiplying 2 powers with the same, I'm multiplying 2 radicals, and so they're both square roots, and so I can write this as a square root of a to the power of 4 times a to the power of 1 is a to the power of 5. All right, so lastly, I want to, without a calculator, arrange these values here from least to greatest. I say without a calculator because there's nothing inherently wrong with the idea of just going to a calculator and decimalizing root 37, decimalizing 4 times the square root of 2, and so on. But we don't need a calculator. And so how can I put these in order with confidence without just going to a calculator? Well, if I make them all entire radicals, it's really, really easy to compare. For example, root 37 already is an entire radical. 4 root 2, if I change the 4 to a 16, or sorry, root 16, I should say, times root 2, I have the square root of 32. So I now know that 4 times the square root of 2 is the same as the square root of 32. How is that helpful? Well, I know the square root of 32 must be less than the square root of 37. I don't actually care what it is in terms of a decimal. I just know that the square root of 32 must be less than the square root of 37. And so far I know the order of these two. What about 6? Well, 6 whole is the same as root 36. So now I know by looking at these three that so far this is the smallest, second, and this is the largest so far. Like I said, once they're all entire radicals, it's easy to compare. And here's the last one, 3 root 5. Change 3 to a radical, which is root 9. Multiply these together, I get root 45. And so now if I look at all these together, it's very, very obvious what my least is. The least is root 32, or actually 4 root 2. So 4 root 2 is my smallest. Next is the square root of 36, or 6. Next is the square root of 37, which is how it was given. And the largest value here was the square root of 45, or 3 root 5. There's them from least to greatest. And again, this may feel like review. Working with radicals like this is an optional part of Math 10, so this may be review, but it's not an expected part of Math 10. And so whether or not, if this does sound familiar, that definitely makes it easier. Either way, we're at a good place to stop this, to come to an end for this first lesson on radicals.